Today, we are going to talk about formal models of distributed systems. So what is a distributed system? A distributed system is a set of nodes or processes. They send message over a network. So here we have a system consisting of 4 nodes. And these nodes are connected by a channel, and they send messages to each other over these channels. And they're supposed to work together to solve a certain common goal. So how do we model these kind of systems? We will model the system by first modeling the behavior of a single node, and then we will put together multiple nodes into a system, which would be a distributed system. So a single node has a bunch of neighbors, and the node can send message and receive message from these neighbors. A node can also do local computation. We will model a node by a state transition system. So the execution of a program or an algorithm computation running in this node will be modeled by a state transition system. And a state transition system is very much like a finite state machine, except that the number of states are infinite instead of being finite. So what is a state transition system? A state transition system consists of a set of states and a rule for moving from one state to the next state. If you move from one state to the next state in a deterministic way, we have a function. Otherwise, we will have a relation. We have also a set of starting states. Okay? Fine. Here is an example of a state transition system for executing a sequential program on a single node. So this is not a distributed program, but just a sequential program running on a single node. And you can see the program here. And the corresponding state transition system. You can think of this as follows. When you start the execution, you are in this point. This is at state S0. And it means at state S0, we have the variable have the value 0. And you go into the loop. After executing this statement, you are at state S1. And the variable has the value 1. And then the variable now will be, next time will be incremented to 2, and 2 you get out of the loop. So you move to state X2 here, the next time in the loop. And when you get out of the loop, you move to this point, which is state X1 prime. So the system consists of a set of states, and this set consists of states X0 to X1 prime. And the state transition function is a function that takes you from one state to the next. For example, from state X1 to state X2. The initial state of this system is X0. When we model a node in a distributed system, this node communicates with its neighbors. So there is also a notion of channels connected between this node and the neighbors. So we can think of a node in a system like this one as having an input buffer. This input buffer receives the messages coming in from other processes, other nodes, and an output buffer will send message to other nodes. And then you have the local state, which we call it here relevant data data relevant to the algorithm. And the initial state of a node, we will consider that the initial state of the node is the state when the input buffer is empty. Okay. Here's an example. So looking to node P2. Node P2, initially it has a local variable, a local state. That's the variable x. It has an output buffer which is empty, an input buffer which is empty. This node received a message from another node. In this case, it received a message M0 from on actually channel 1. So it moved from this state to that state. And that state is a state where it has a message on the input buffer and the variable, local variable is still 0. At this point, this node did a computation step. And this computation step resulted in sending a message, which is a message on the output buffer, and incrementing the variable x. And we move from one state to another this way. Okay, so this we move. So what is state transition functions? The state of a node, except the output buffer, is called the accessible state of a node. And I think this is clear why. Because when a node does a computation step, it depends on the message received on the input buffer and the local variables of that node. And that part of the state, so we are removing now the output buffer, that part of the state is called the accessible state. So a transition function f takes accessible state and creates a new state. And it removes at most one message from the input buffer and adds 0, 1, or more new messages to the output buffer. And possibly it will modify the local state. The messages on the output buffer are also tagged with the destination node. So state transition functions. So the state of a node, except its output buffer, is called the accessible state, as we just said. Here's an example. A node has a local state, which is the variable x, and an input buffer with an incoming message M0. And a state transition function f will take the message and the local state, transform it to a new local state, and possibly produces some messages in the output buffer. So if we look to the state transition function, we want to define it formally. So the state will be a triple. The triple consists of the local state, the set of messages on the input buffer, and the set of messages on the output buffer. So, a state transition function, what does it do? F. So it takes the input state, which is the current state, the set of messages on the input buffer, and the set of messages on the output buffer, and transforms this in one step to a new local state, a new state of the input buffer, a new state of the output buffer. And how does it do it? It does do it by removing a message from the input buffer, computing a local function. This function takes the input state and the messages removed from the input buffer and produces a pair, which is the output state, the resulting state, and a set of messages that it has produced to send. Then it adds the set of messages to the output buffer. Okay. So given this, so we can think of a computation on a single node. So what a computation on a single node do? So a node waits for message typically, and then when it receives the message, it does some local computation, and it sends some messages, and it continues. And we call this sequence of actions a computation step. So this reflects what we want to model. This is something that you can ask yourself and see if that is correct. But you can see, does it really model determinism in the sense that each node is executing in a deterministic way? And does it model atomicity in the sense that what it does when it picks a message from the input buffer, do some computation, and produces some output messages, does it do it in an indivisible way? So just please answer this question. So now we move from a single node to set of nodes. And a set of nodes describe a distributed system. So we are going to compose the state of the system from the state of each node. So a configuration, which is the state of the system as a whole, will be a snapshot of the state of all nodes. So the configuration will be a snapshot of the state of every node. So this is the state of node 0, this is the state of node 1, and this is the state of node n-1. And an initial configuration is a configuration where each node is in an initial state. And we know what's the initial state of a single node, so now we know the initial state of a configuration. Here is a configuration for nodes P1, P2, and P3. And here is the state of each node. And this could be very well be an initial configuration, because initial configuration only requires that the input buffer to be empty for each node. So the system evolves through events. And what are the events in the system? That's very easy. I think you can think of a distributed system. What are the events? A node makes a computation step. We call this a computation event, and we denote it by comp I, and this is computation event happening at node I. Or it could be a delivery event. And a delivery event takes message from some output buffer of some node and deliver it to the destination node, deliver it to the input buffer of the destination node. So now, how we do a computation event? We just apply the transition function f on the node i's state. And how we do a delivery event? See the delivery event from node I to node j of message m. We move the message m from the output buffer of node I and put it into the input buffer of node j. So given now, we know what are the possible events in the system. Are computation events performed by processes, or delivery event performed, you can say, by the network. So what is an execution? An execution we can model the execution as a sequence. And in fact, we will see that we will have an infinite sequence of nodes, of events, of course. And an execution is basically a sequence that starts with a configuration, perform as an event, transform the configuration to a new configuration, performs an event, transform the configuration to a new configuration. So here we can say, with this we think of it like a timeline. So what we are doing is, here is the initial configuration, which we call it config 0. We perform an event. So this is, we call it event E1. This transforms the configuration to another configuration. We call this config 1. And we continue the same way. So we perform another event, and so on. Another configuration, and so on. So, and if the event is a computation event, so we are going to transform our configuration, say in this case k-1 to configuration k, by applying node i's transition function on the I state in configuration k-1. So after performing a computation event, what will happen is that only the state of node I will change. Possibly one message is removed from the input buffer, the local variables are transformed, and some messages are added to the output buffer of that node. The state of all other nodes are not changed. And if it is a delivery event, we just change the configuration from one state to another by moving a message from the output buffer of node I and delivering to the input buffer of node J. So what you can say here is that if we have number of nodes, here is the state of the nodes Q0, Q1, and Q2. A computation event, say on Q0, will transform the state of node 0 and keeps the state of other nodes unchanged. Whereas, if it's a delivery event, say a delivery event from node N1 to node N2, it will transform the state of the involved node by changing the output buffer of node 1 and modifying the input buffer of node 2. So here we get transformation of the state of these two nodes. So this happens if we do a delivery event, and this happens when we do a computation event. So here is an example. The example is we do a delivery event from node 2 to node 3 of message M. Here is our node 2, and we can see here that is the node 2, the message is removed from the output buffer and the message is added to the input buffer of node 3. And a computation event, this is a computation event on node 3. We just transform the state of node 3. So an algorithm has many executions, and every execution is described by a sequence of events. So I will leave to you now a question to answer, and why we model execution by a sequence of interleaving of events.